you. Thank everybody that is here. And I'd like to thank the organizers for the kind invitation to present this recent work. And this work that I've done in collaboration with Gustavo de Brito, which is my co-supervisor here in Denmark, in the University of Southern Denmark, and also my supervisor, Antonio, in Brazil. This work is based on this paper that was published in PRD and talks about the fate of chiral symmetry in Riemann-Cartan spaces. So I will define both concepts. So my brief outline is, well, I will try to comment a little bit on what is chiral symmetry breaking, to refresh everybody on what is this and how it is related to gravity. And then I will focus more on how it is connected, how it can be studied, especially the mechanism of chiral symmetry breaking studied within a curved background. I will focus first on the curvature-induced gravitational catalysis, what is known as gravitational catalysis. I will define later. And then I will move to the actual topic of the paper, which is torsion-induced catalysis, or if this mechanism exists or not. And then I will move to the conclusions. So as a reminder, so chiral symmetry, especially chiral symmetry breaking, is deeply connected to generation of fermion masses. So for instance, let's focus on a fermion which is composed of one flavor fermion, and we compose it to its chiral components, so left and right. And if you perform a simple U1 axial transformation, you see that the kinetic term is allowed by this transformation, but the mass term breaks this chiral transformation. So the existence of massive fermions is an indication that some sort of chiral symmetry has to be broken. And this can happen either by explicitly, so for instance, by explicit term in your Lagrangian, like a mass term in your Lagrangian, or it can be broken by through a mechanism of spontaneous or dynamical breaking. And it's this second mechanism that will focus from here on. So and let me discuss where we find chiral symmetry breaking in nature. So one example is in QCD, and we know that the proton, for instance, is composed of 3 quarks, but the mass of each individual quark is around a few MeV. But collectively, to compose the proton, we know that the mass, the proton is way bigger, is around 1 GeV. So there should be some kind of mechanism to generate this additional mass. And this mechanism is as roughly 99.9% of the mass of the proton is non-perturbably produced in QCD by the dynamics of quarks and gluons. And this can be seen by the quark mass function in the right panel. This is done in a Dyson-Schwinger computation, and we see that the mass function for the quarks, focusing, for instance, in the up and down quarks, the lightest ones, are around a few MeV for large momenta. But if you go to a small momenta, you see that the mass function is larger by several hundred MeV. And this is the scale of the quarks, of the constituent quarks, and also by other hadrons. Another example where you can study chiral symmetry breaking is in condensed matter systems. Here I'm picking the example of planar Dirac fermions under external magnetic field. And if you apply an external perpendicular magnetic field on a system with planar interacting Dirac fermions, you see that this external magnetic field induces chiral symmetry breaking, as it serves as a catalyst for chiral breaking and consequent mass generation. This is known as magnetic catalysis. And this is rooted in the change of the spectra of the Dirac operator. And essentially, you have a non-vanishing chiral condensate. And in order to compute this chiral condensate, you see that it is proportional to the magnetic field. And the magnetic field essentially removes two spatial dimensions. So you have an effective dimensional reduction. And this is one of the mechanisms behind this magnetic catalysis. But we are actually concerned with this mechanism in gravity. And as any matter field that propagates through space-time, it's actually conceivable that gravity changes the space-time geometry in which all these fields propagate. So the background structure of the space-time will change the spectra of the Dirac operator. And this will ultimately cause an effective dimensional reduction as well of the fluctuation spectrum. And this is an effect that is enhanced in hyperbolic spacetimes. And this, in turn, can also affect the chiral breaking mechanism. And if you are in a curved spacetime, then this is similar to the magnetic catalysis. And inspired by those, it is called gravitational catalysis. And this has been studied a lot since the 70s and the 80s. But one simple question is, how can we identify the chiral breaking, especially more generally, how can we identify chiral breaking in general? But I will focus here on a system which is composed of a Nambu-Jona-Lasino type model. So it's composed of a Dirac kinetic term. This is in flat spacetime for starters. And it also is composed of fermionic interactions in the form of the V plus A channel. So the V channel is composed of vector currents, and the axial channel is composed of axial pseudo vector currents. And we can study the chiral breaking in this system by analyzing the renormalization group flow of this quartic coupling, which is lambda. And at one loop, and disregarding the anomalous dimension, we see that the beta function for this quartic coupling is written like this in 4 dimensions. And if we integrate this beta function from a UV scale down to an infrared scale, we see that it has this form, and we can actually plot this quartic coupling as a function of the cutoff scale, and it has a fixed point which coincides with the critical coupling in this case, which is constant from the UV to the IR. But the interesting part is if you start your flow from the UV in a regime where the quartic coupling is smaller than the critical value, then you see that all the trajectories lead to the infrared, the finite value in the infrared. So the quartic coupling doesn't diverge. It decreases along the RG flow to the IR. On the other hand, if you start your flow with the quartic coupling larger than the critical value, then see that at some point, at some scale, you reach a divergent coupling. And this is related, or this is a signal of the onset of chiral breaking. But in order to study this in a different angle and to make this connection more clearer as to why this is connected to chiral breaking, I would like to discuss this other picture, which is the partial bosonization of this system, which essentially means that we are trading a four-fermion interaction by a Yukawa-like interaction. And this procedure, which amounts to introducing at the level of the path integral additional complex scalar fields, allows us to connect this RG picture with the more directly with the spontaneous symmetry breaking picture. And why is this? Because when you introduce this by using this famous Huber-Stratonovich transformation, you introduce this mass term for this auxiliary scalar field, and so if lambda is divergent at some cutoff scale, it means that this mass term will be the sign of this mass term will be flipped, which is an indicative of spontaneous symmetry breaking. This can be studied through the method of the effective potential. So essentially, you integrate all the fermions, but the effective potential at some during the computation, you see that it has quadratic divergence, logarithmic divergence. So at some point, you have to regularize the theory, and we choose to regularize it with an FRG-inspired cutoff function, and we can plot this potential as a function of the configuration field, and study the structure of the minima of the potential. And if the potential develops non-minimal, non-trivial minima, then this is as an indication of spontaneous symmetry breaking. And this is rooted in the second derivative of the potential near the origin. And you see that if you focus on the first two terms in the parentheses, if lambda is less than the critical value, then the first term is positive, and all the remaining terms in the parentheses are also positive, and so there's no development of minima. And this is valid for all values of the cutoff scale. On the other hand, if you consider that the quartic coupling is larger than the critical value, then the first term in the parentheses is negative, and there should be a transition scale below which the potential develops non-trivial minima. So you start integrating your fermionic modes from an arbitrary large cutoff scale, and then you, as you go to zero, you see that the potential develops non-trivial minimum. And this is the indication of symmetry breaking, and is connected in this way with the previous picture. Moving on to a curved background. So we consider the same system, but now in a curved background. And the difference, the main difference here is that in the modification of the Dirac operator, because now the Dirac Laplacian gets modified, as you know, by this additional term proportional to the Ricci scalar, and that expression for the second derivative of the potential also gets an extra piece proportional to the Ricci scalar. And now the situation is a little different, because no matter what the relation between the quartic coupling and the critical value is, if the curvature is negative, then the second derivative of the potential can be negative for sufficiently small values of the cutoff scale. So if the curvature is negative, you can choose. There's always going to be a sufficiently small value for k, which makes the contribution of the curvature dominant over the rest, and for negative curvature, you will have curvature-induced parasymmetry breaking. This is an example that I've taken from this paper by Holger and Ricardo, and especially this result is in 3 dimensions. They also performed the same analysis for higher dimensions. But however, most of these studies were actually based on gravitational catalysis, whereas we're actually focused on metric-based formulations. So what I mean by this is all of your geometric objects were characterized by the metric. So the affine connection, the curvature, the covariant derivatives, and so on. But as some of you know, different formulations of gravity can lead to richer structures. And one of the most general ones are the metric affine gravities. So you can allow to have the metric and the affine connection being treated as independent degrees of freedom. And now your curvature and covariant derivatives and so on are also depend on this affine connection. And you can study different particular cases. So for instance, I'm showing here the situation where you have torsion, which is connected to the affine connection being antisymmetric. So if you don't have torsion and you have no metricity, then you have symmetric metric affine gravity. But you know, in the other direction, if you turn off the no metricity tensor, you reach antisymmetric metric affine gravity. And if you switch off both, then you get standard general relativity. So for this talk, I will focus actually on the last, on some version of this antisymmetric metric affine gravity. And this version is called the Einstein-Cartan formalism, and is based on more fundamental and independent objects, which are the Vierbein and the spin connection. And to the Vierbein, you can generate the metric tensor. So the metric tensor is seen as a composite field formed out of the Vierbein. And in this sense, there is an isomorphism between the tangent space of your manifold and the coordinates, the space-time coordinates. And this is made by the Vierbein. The affine connection can also be obtained by the Vierbein and the spin connection, which is the omega. And the spin connection is the gauge field of the local Lorentz transformations. I should be careful here because all this analysis that I'll be doing, I'll be in an Euclidean setting. So actually, the spin connection is not the gauge field of the local Lorentz group, but the local orthogonal group. Okay, and one comment here is that in 4 dimensions, this is the typical formalism that one uses in order to couple fermions to gravity. So, for instance, in 4 dimensions, if you want to couple fermions to the Einstein-Hilbert action, this will lead to a relation between the torsion and the fermion bilinears. But the relation to the torsion is proportional to these fermions, and the proportionality constant is actually the inverse of the Planck mass squared. So you see that this torsion-induced interaction is highly suppressed, at least at the classical level. So we cannot say, from this type of calculation, we cannot say anything about the quantum level. Yeah, as I was saying, the Vierbein formalism is the typical, but not the only one, the only way to couple fermions to gravity. So some of you know there is the local spin-based formalism, and maybe other ones that I'm not aware of. But that's the formalism that we choose, and we stick to it. And well, the extension of the Clifford algebra to the curved space is straightforward. Is given by the mapping between the Vierbein and the curved Dirac matrices. You can define the Dirac matrices on the tangent space, and the coupling of fermions to Einstein-Cartan gravity is very straightforward. So I'll be spend so much time on this. So you write your standard kinetic term for the Dirac action in this covariantized way, where you write this in a manifestly Hermitian way. I'm fleshing out the covariant derivative, the convention that I'm using for the covariant derivatives. And the nicest thing is that actually you can split the spin connection between a torsionless part and a torsionful part. the torsionless part, which is this omega with the open circle on top of it, is fully determined by the metric or equivalently the Fibonacci. And the second term, which is the contortion tensor, is fully determined by the torsion. And this the contortion term is actually the piece that will bring the torsion into the game. And this will bring this modification to the covariant derivative. So now the covariant derivative will be split into the standard curved space covariant derivative and this plus a term proportional to the contortion. If we do the calculation explicitly, you will see that the only component of the torsion that gets excited in this that is included in this calculation is the totally antisymmetric component, which is given by the axial vector that I'm calling A. So finally, you can rewrite the Dirac action in this way. So you have the standard curved space Dirac action plus the interaction of the torsion with this fermion bilinear. And it comes with the gamma 5 matrix. And this combination, this contribution will give a modification of the covariant derivative acting on the fermions, and will ultimately give a modification for the effective potential that we'll discuss in a minute. So this is one way that torsion can appear in this scenario. This is maybe a minimal way. So the system that we considered was this system plus for fermion interactions. So a form of Nambu-Jona-Lasino model in Riemann-Cartan formalism. So performing these simplifications, which are not approximations, you end up with this action right here. And if you go one step further and perform a Hubbard-Stratonovich transformation as well, you end up finally with this Lagrangian, this action. And this is the action that will that's the setup of the work. So the next question is, so how does torsion affect the fate of chirosymmetry? As we did for flat space and also for curved space, but without torsion, we can compute the effective potential. Also, in this case, there will be divergent terms proportional to, quadratic divergent terms and logarithmic divergent terms. So you have at some point to regularize the system, perform renormalizations and so on. So, and one method that we choose is to follow the FRG techniques. But now the coarse-graining operator is defined by this operator, and it contains this the B and the X operator, which is complicated ones. But I mean, not so complicated, it's straightforward. And the next step is just to compute the second derivative of the potential, because this is the quantity that will be relevant for the analysis of chirosymmetry breaking. And in particular, we have to study the cases where the second derivative will be negative near the origin, of course. But as we were progressively doing the computation, we saw that it would be helpful to consider two different regimes. The first regime will be treating both curvature and torsion, and parenthesis here. Whenever I say curvature, I mean this the scalar, the Ricci scalar, or some combination of curvature. And when I say torsion, I mean only the actual component of torsion. So, so the first regime is both curvature and torsion much less than than the cutoff scale. So so very tiny quantities. And in this regime, you can actually use the early time heat kernel expansion to evaluate the trace. And this regime allows us to carry the combined effect of both background curvature and torsion, but it has the caveat that it's not applicable in the infrared regime. So because of this, we considered another regime, which is disregarding the curvature and focusing on the torsion, and as an approximation, considering that is approximately homogeneous. And in this regime, it's possible to evaluate the trace in an exact fashion. So yeah, and then for this approximation allows us to investigate the impact of this background torsion in the deep infrared regime. So for the first regime, we used the standard early time heat kernel expansion. And since we are focusing on small amplitude values for the curvature and torsion, we can actually truncate the series and disregard higher order contribution in torsion and curvature. This, as I will comment in a moment, will bring some advantages and disadvantages. The disadvantages that we cannot actually access the deep infrared regime, but I will comment this on later. With this, then we can actually compute the potential, the effective potential, and since we are interested in the second derivative, we can compute it very straightforwardly. And we see that this expression depends on various terms. So the first term is related to this UV scale lambda, and it is identified with the critical value of the quartic coupling, and it's proportional to the to this I2 integral. This is a threshold integral, and it captures the dependence on the cutoff shape function. In turn, this threshold integral is of order 1 in all the calculation that we've done. There is the second piece, which is the proportion to the logarithm of these UV this UV scale, and this can be eliminated by a renormalization of the non-minimum operator in your Lagrangian. So you can actually introduce a counter term in your action. This counter term is composed of both the curvature and combination of torsion squared terms. And this will allow to remove this divergence by the introduction of this extra coupling, this psi right here. This psi will be an external parameter, which ultimately will have to be fixed by an external experiment. The last piece, which applies the logarithmic, is the trace of the second kernel coefficient, which is proportional, which is exactly given by this combination of the curvature and the axial torsion. And I should say something about this notation in this. It's not an expectation value, but it's more like a space-time volume average over your manifold. So this is the expression for the second derivative of the potential. And after some simplifications, you get this. And it resembles the case where you do the same analysis on a curved background with just curvature. But now you get this extra piece. So you see that as in the previous case, there should be there should exist a transition scale such that the potential, the second derivative, will be 0. So at some point, the second derivative will be positive, and then you will have to transition to a negative values So in this transitional pass, you will have to reach 0. So there should be, it's conceivable that there should be a transition scale. And it's straightforward to compute this transition scale, and it's given by that equation on the right. And this transition scale should be positive. And in order to do so, I mean, before I comment on the implications of this, you see that it only makes sense of the transition scale, it only makes sense if it's positive. But if as a first analysis, you can disregard the curvature and torsion, and you just end up with a flat space calculation, which says that for lambda greater than its critical value, you have chiral symmetry breaking. The next analysis is if you only consider curvature, but you disregard completely the torsion field in the axial component. And you see that if you look at the transition scale, then since the curvature comes with a negative value, then negative values for curvature will actually increase the transition scale. And if the transition scale gets increased, then as you integrate your fermionic modes, then you essentially reach the transition scale earlier. So in other words, you reach chiral symmetry breaking earlier. On the other hand, if you consider positive values for the curvature, then this transition scale gets lowered. So this acts against chiral symmetry breaking. So bottom line is curvature, negative curvature acts in favor of chiral symmetry breaking. The other situation is when the curvature is 0 and you only consider the effects of torsion. And in this case, since the contribution of torsion comes with a plus sign, then arbitrary large values will of this axial torsion contribution will actually increase the transition scale. And the thing is, this is an exact result as I was saying previously. But all this this analysis is assuming that this parameter xi is positive. If you consider that this parameter is negative, then the whole picture changes. And one thing is that I should comment is all this calculation was done in Euclidean setting. So in this case, the contribution of torsion is positive definite. So if you go to a Lorentzian, if you do the same analysis in the Lorentzian manifold, then you should be more careful because it's not straightforward to get to extract these conclusions. So those plots is just to confirm what I have talked about previously from the effective potential, and you just so the left panel is all the colored region is the region where you have chiral symmetry breaking triggered by these quantum fluctuations of curvature. So the first panel is disregarding the torsion contribution, and you see that as you go to the lighter regions, which means negative curvature, you see that there are more and more region that is allowed by chiral symmetry breaking. On the other hand, if you go to the case where you just disregard curvature and just focus on torsion, then the region for chiral symmetry breaking gets bigger as you consider more and more positive values for the torsion. And this is in agreement with what we have previously discussed from the analysis of the effective potential. But this is not the final word yet, because as I was saying, we have to consider this regime where you only consider small amplitudes for curvature and torsion. And this amounts to truncating the series in the heat kernel expansion. So the higher order terms, however, will be important and more relevant as you go to the deep IR. So this analysis that we've done is not capable enough to reach this deep IR sector. So maybe another technique, a late time heat kernel expansion, or another technique will be actually needed for this to reach this. And if this is possible, then the deep IR sector is essential for the occurrence of gravitational catalysis. Because what we have done so far is just it was a study of viability of carrier symmetry breaking. But if in order to see that if torsion actually torsion and curvature combined will actually induce carrier symmetry breaking, we'll have to access the deep IR sector. If we manage to do this at some point, then that transition scale will be modified by this f function. This f function is a general function built from the curvature and torsion, and it encodes terms that go beyond the early time expansion. And this f function will be dominant in the IR. And you can see that if it's positive, then it also triggers carrier symmetry breaking. I would like to add a comment on the teleparallel theory, because one may argue that, well, you're studying carrier symmetry breaking in spacetimes with curvature and torsion, but there is a nice formulation which already includes torsion, and actually the spacetime is characterized only by torsion, which is the teleparallel formulation of gravity, or the Weizenbach teleparallel gravity. So in this formulation, you only consider torsion, so the curvature and non-metricity are both vanishing. And you can define a special spin connection, which is called the Weizenbach spin connection, which I'm denoting here with a closed, a full circle on top. And this, in terms of the spin connection, you can compute the curvature, and this curvature turns out to be 0. But there is a relation between this Weizenbach spin connection and the Levi-Civita spin connection, which is given by this equation right there. And if you want to study this, if you want to follow the same procedure that we did, but in this teleparallel theory, the prescription of minimal coupling of fermions to gravity is done like this. And you see that the combination that appears in the covariant derivative regarding the spin connection, the contortion, are only regarding the Weizenbach spin connection and contortion. But if you look at the above equation, the combination is just the usual Levi-Civita spin connection, the torsionless spin connection. So essentially, the minimal coupling will be the standard Riemannian minimal coupling procedure. So in this sense, no torsion contribution appears if you want to study the fate of carrier symmetry in teleparallel formulation. And ultimately, the mechanism of gravitational catalysis is equivalent to the one in Riemannian manifolds, and which I cite here once again the work by Holger and Martini and Ricardo. So moving on to the conclusions and outlook. So torsion seems to act in favor of carrier symmetry breaking in systems of fermionic interactions, which means that it increases the region in parameter space of the quadratic coupling and the critical coupling. But again, this is an analysis that it has some limitations. You have because we weren't able to go beyond the small amplitude analysis, and this required actually more work to be done in order to determine the fate of gravitational catalysis, because the the actual answer is only done if you can combine both of the effects of curvature and torsion. So there are effects at the same time. As an outlook, and as a way to try to circumvent this, we actually probing the effects of dynamical gravitons and propagating torsion fluctuations on the mechanism of gyrosymmetry breaking. And this is a work that is being done by Gustavo and myself, and will probably appear in the near future. And in this case, we are actually trying to go beyond this limitation of considering small amplitude, and also considering the effects of propagating torsion degrees of freedom, because in this work, we didn't include any propagating torsion effect. And it seems like it should be the propagating torsion, I mean, it's something delicate, but and it's something that it has been, I mean, overlooked in the literature at some point. So it's something that we are interested in, and probably will allow us to get some conclusions that this using this approach we're not able to get. Another thing is, it would be interesting to study gyrosymmetry breaking in condensed matter systems, because there are some condensed matter systems which exhibit curvature and torsion-like effects, and those are defined in terms of topological defects. So you can actually emulate curvature and torsion in systems in systems in 2+1 dimensions, for instance. And one hope within this program of analog gravity is to try to see if you can study this, use this framework of probing gyrosymmetry breaking in this more controlled tabletop experiments. Yeah. So with this, I thank you for your attention.
Thanks a lot, Arthur, for the nice talk. All right. We do have time for some questions. So if you have a question, please raise your virtual hand or your actual hand. And I already saw Aaron.